So there's a very interesting question that arises, and this is fundamental to design of virtual reality headsets. If I put a display in front of the eye like this, how much resolution is enough? Right? How much resolution should this display be, given that I know the photoreceptor density from this plot and from these pictures I've made? We should be able to do some simple calculations and just try to estimate. So why don't I do that just to give an idea, because you see this around. People in industry are talking about how much is enough. I think it's quite difficult to say without doing the experiments. So somebody has to manufacture high resolution displays higher than 1080p. I mean something like 2K by 2K per eye, and then maybe 4K by 4K per eye, and maybe 16K by 16K per eye, and so forth, and see where the limits are, right? That's the kind of things that should be done. So how much resolution, let's say a display is enough for VR. Like I'll leave my picture right here that I made. Let's suppose, I guess I'm all the way off at 50 degrees from the picture I have remaining, but even if this were at the fovea, let's say, and we return to the other picture, then if I had very low resolution in this optical system here, then the pixels, think about one individual pixel there, like a kind of a square, let's say. They don't really look like that, but let's suppose they're perfect squares and they get imaged on the retina somewhere. So if that's the case, if the resolution is low, there will be this pixel that gets projected onto the retina, and then there are a lot of photoreceptors to detect it, right? And as we increase the density of the photoreceptors here, if we're close to the, if we're at the fovea, let's say, we may have a lot of photoreceptors, so you perceive there's a square there, right? You're seeing what's called the pixel structure. Now it's not exactly a square because and you can do this after class if you like. You can use the same magnifying lens, walk up to this screen over here and take a look at the subpixels if you've never done that before. The R, G, and B components are interlaced in some kind of way, so they don't make, it's not, there's not exactly one RGB rectangle, right? So you have to go in and look at the even lower or even higher resolution, which is even smaller contributing components to the images that we see. Well, here's one thing I could do. I could make a rough estimate and say we have 126 million photoreceptors, right, total, because I said we had a, what did I say, 100 million, no, 120 million, which one, cones or rods? 120 million cones and about 6 million rods, or is it the other way around? 120 million rods and about 6 million cones. Good, okay. Because the cones are all concentrated, as you can see from the picture, the cones are all concentrated around the fovea, but then the rods, there's quite a lot of them and they're distributed over a much larger area. So it makes sense that there are significantly more rods. Well, I could just take the square root of this, and that's roughly equal to 11,225. And if I imagine now, why did I take the square root? Well, let's just imagine that the retina, if I were to unwrap it, it's really a spherical cap. I'm just imagining unrolling it and flattening it out. So if I were to do that, okay, it doesn't have a square shape, but I'm just trying to make a very rough estimate here. So if I were to do that, trying to imagine what a rectangular screen should look like, then perhaps it should be 11,000 by 11,000 roughly. If I wanted to have the total number of pixels that I present to an eye match the total number of photoreceptors. Is that even a good idea? I'm not sure. Right, so we could adjust further and say, well, why don't I just take the area of highest visual acuity, which is around here, and because I'm going to have the fovea, let's say, aimed at the place where I'm looking most of the time. So why don't I say, okay, that's going to be the place where I'm going to be looking for pixels, so maybe I should use that, right? So I could make a more careful calculation. I could say the density at the fovea and I'll even round up a bit. I'll say it's about 200,000 per millimeter squared. Right. So if I look at it that way, turns out that the area of the retina is, I looked this up before class, this is 1,094 millimeters squared. Of course, there must be some variations among humans, but 1,000, so roughly 1,000 square millimeters. So if I imagined that the retina had maximum density in all places, well, that's kind of a strange assumption. Why would I do that? I'll say why in a minute. But if you imagine that this is the limiting case, then if I take the square root of the 200 million that I get, because if I had maximum density and I had it spread across, let's say, roughly 1,000 square millimeters, then this would be about 200 million photoreceptors. And if I take the square root of that, this is about 14,000. So a little bit bigger. And what's interesting about that, the reason why I tried to look at the case of imagining as if the fovea were propagated across the entire retina. In other words, imagining that the fovea were so large it has that top density, the highest density of photoreceptors everywhere, is because this eye can rotate. Right? So you can rotate the eye and look at the top and bottom of the screen as you rotate. So it effectively becomes like that, right? If you're trying to ask how high the resolution of the screen should be. So this is reasonable. So maybe a reasonable upper bound, maybe a 16, let's say 16K by 16K display per eye should be sufficient. Should be sufficient for not perceiving pixels. Now at this point you might ask, why don't I just track which way the eye is looking and then only present that highly dense information exactly in the right place where it needs to be, and don't worry about the rest of the image, right? And that would save a lot of effort in computer graphics, a lot of effort in trying to put out so many pixels across this entire display. All these pixels will be rendered here on the off chance that your eye is looking at them, but it doesn't know where your eye is looking, so it just has to render all of them. So a great idea, it's called foveated rendering. Foveated rendering, right, is to track the eye and then only draw high resolution images in the place where we know that the eye is looking, where the fovea can perceive these areas of greatest concentration, right? So, and that's all fine. It's more expensive to do the eye tracking, and it introduces latency into the pipeline. So there's tracking latency, and then you have to do customized rendering for that. Maybe a few years down the road that'll be feasible in the consumer space of products and things, but for right now it's not effective enough at low cost, and may not even be effective enough at a very high cost, but it's right on the kind of thresholds, let's say. Questions about this? Now sometimes I look at this and I feel motivated to go even higher and say, well, maybe it should be 32K by 32K, because I looked at the number of photoreceptors, but I did not take into account the fact that there's RGNB photoreceptors, right? So maybe I should imagine, well, I need to have enough to wait, which way should I go in that case? Let's see. I don't have this density of RGNB photoreceptors. I actually have a lower, if I just pick one of them, of just reds, I have a lower density of them, right? And also when I look at my display, it has some kind of pattern of RGNB components as well. So I've not taken into account the patterns of RGNB here and the patterns of RGNB here, right along the retina. So I have not even taken that into account. If I take that into account, would this estimate increase or decrease? Perhaps it would decrease. Yeah, it may decrease. This may be sufficient, let's say, overkill. And an interesting question is, if I were to make a 4K by 4K display, would that be enough? Would you ever be able to perceive anything? Would there be any need, right? Would you ever see pixels at 4K by 4K? And you know, the honest answer right now is I don't know. I've never experienced it before, and I cannot say. Right? I feel fairly certain that at 16K by 16K per eye, I would not perceive pixels. But you know, the brain and the human vision system is often full of surprises. So who knows? But it seems that this should be sufficient. Questions about that? Yes. Yes. There is some asymmetry. I believe it corresponds to which eye this is. And I'm afraid to be quoted on this, but I believe you go further in this direction, which I would guess for evolutionary reasons is that something may be coming from this side to eat you, and it's better to see as far as possible, whereas your nose tends to block this side anyway. And then it's asymmetric. You know, it's the mirror image for the other eye. So that's why I believe it's asymmetric like that. Anyone else? It's good. I wondered it myself a few months ago, and I looked it up. I believe that's the answer, but could be wrong. All right. Let me say a little bit more about photoreceptors, and then I want to start to get into the visual pathways, let's say, that lead from photoreceptors up to your visual cortex. So I want to say a little bit more about photoreceptors as we go along here.